Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, like GPT, GLM, and Llama, which have significantly improved various real-world applications. One complex task they enhance is long context question answering, LCQA, which involves reasoning over lengthy documents to provide accurate answers. Recently, models such as Gemini and GPT-4 128K have emerged, capable of processing entire documents. However, they often struggle with the lost in the middle problem, where relevant information located in the middle of a document leads to subpar or incorrect answers. To address this, we look at the Retrieval-Augmented Generation (RAG) system, which uses a fixed-length chunking method to keep inputs concise and relevant. Despite this, vanilla RAG has two main limitations for LCQA. First, chunking can disrupt the context and background information, leading to incomplete data and potentially incorrect answers. For example, it might retrieve the name, Griffin, but miss the university he graduated from, even if it's mentioned in the same paragraph. Second, the presence of noise in long documents can reduce the quality of retrieved information, making it hard for LLMs to find key details. Recent RAG systems like Self-RAG and CRAG have tried to improve these issues. Self-RAG uses self-reflection tokens to explore global information but risks losing valid chunks. CRAG assesses each chunk's relevance individually but may miss connections between chunks, leading to overlooked important details. In our work, we introduce LongRAG, a robust RAG system designed to tackle these challenges in LCQA. It includes 4 flexible components: a hybrid retriever, an LLM-augmented information extractor, a chain of thought (COT) guided filter, and an LLM-augmented generator. LongRAG enhances the ability to extract global information and identify factual details. The long context extractor organizes retrieved chunks into a higher dimensional semantic space, refining the overall context. The COT guided filter uses global clues to help LLMs focus on relevant details, improving the understanding of complex contexts. We also developed an automated data pipeline for creating a high-quality dataset for fine-tuning, which boosts the instruction following capabilities of our system. This makes it easier to adapt LongRAG to different domains. Our extensive comparisons on 3 multi-hop datasets from LongBench show that LongRAG outperforms both long-context LLMs and advanced RAG methods. We confirm its robustness and transferability across various fine-tuned LLMs. In summary, our contributions include: 1. The creation of LongRAG, which significantly outperforms existing models. 2. The identification and addressing of RAG's limitations in LCQA through new components. And 3. The implementation of a novel fine-tuning data construction pipeline that supports diverse applications in real-world scenarios. Section Summary. In this section, we discuss the advancements in long context question answering, LCQA, using large language models, LLMs, and highlight the limitations of existing Retrieval-Augmented Generation, RAG, systems. We introduce LongRAG, a robust RAG paradigm that enhances the retrieval and understanding of global information in lengthy documents, significantly outperforming traditional LLMs and RAG methods through innovative components and a fine-tuning strategy. Section: Related Works. In this section, we discuss related works on long-context large language models, LLMs. LLMs often face challenges with complex and lengthy inputs due to their limited context window, which can lead to performance issues when inputs exceed this limit. Recent research aims to extend the context length of LLMs for tasks like long context question answering. We categorize methods for scaling context length into 2 types. 1. Training or fine-tuning methods that include techniques like RMT, position interpolation, and others. 2. Non-fine-tuned methods, which are generally easier to implement and cost-effective, such as restricted attention approaches and context compression. While non-fine-tuned methods are more accessible, fine-tuned methods usually yield better results but at a higher cost. Next, we explore Retrieval-Augmented Generation, RAG, which has emerged as a valuable approach for enhancing LLM responses. RAG addresses issues like outdated knowledge and inaccuracies by utilizing external information sources, such as Wikipedia. However, challenges remain with the way information is chunked and integrated, leading to incomplete data and noise. Recent advancements in RAG focus on improving the filtering and ranking of retrieved information, reducing noise, and employing strategies to enhance information retrieval. We also note that fine-tuning has become a common method to boost the performance of RAG components. This includes fine-tuning retrieval components for better results and generators for more tailored outputs. Research shows that even a small amount of high-quality data can significantly improve LLM performance, supporting the idea of collaborative fine-tuning across RAG components with minimal data. In terms of task definition, our LongRAG system builds on the vanilla RAG structure, incorporating a long context extractor and a COT-guided filter to gather global and factual information. Given a question and a long context corpus, the retriever identifies the most relevant chunks, which are then processed to extract necessary information for generating answers. For fine-tuning data construction, we create a high-quality instruction following dataset called LRG instruction using a teacher LLM. We select training sets from various complex datasets to enhance our instruction dataset, particularly focusing on those with longer contexts to improve LLM performance. Our automated construction pipeline allows for efficient generation of fine-tuning data, and experiments show that we can achieve good results with just 2,600 samples. In our data pre-processing phase, we eliminate question-answer pairs with insufficient context and retain supporting and distracting paragraphs to reflect real-world recall distributions. We define our pre-processed dataset elements, including questions, corresponding paragraphs, and answers. For the long context extractor, we fine-tune it to better extract global information from source paragraphs. We treat all supporting paragraphs as effective global information and use them for zero-shot in context learning to establish a strong foundation for our outputs. We validate these outputs with a self-evaluator to ensure their reliability. For the COT-guided filter, we construct training data in two stages, generating guiding chains of thought, COT, and filtering. We focus on the supporting paragraphs to derive insights for question resolution, using a self-evaluator to confirm the quality of the COT outputs. In the filtering stage, we combine the question with its corresponding paragraph and guiding COT to create our gold data. Finally, we organize the existing question-answer pairs and paragraphs in our dataset to align with our task-oriented goals. Section Summary. In this section, we discuss advancements in long-context LLMs, highlighting methods to extend context length through fine-tuning and non-fine-tuned approaches, as well as the role of Retrieval-Augmented Generation, RAG, in enhancing LLM performance by integrating external knowledge. We also outline our LongRAG system, which incorporates a long context extractor and COT-guided filter to improve information retrieval and answer generation, and detail our automated process for constructing a high-quality instruction following dataset for effective fine-tuning. Section: Hybrid Retriever. In this section, we describe our hybrid retriever, which starts with a question and retrieves a set of chunks. Before retrieval, we break down the long context into smaller chunks, ensuring that sentences are the smallest units. We use a sliding window approach to add overlapping content from the end of the previous sentence, which helps maintain meaning at the cutoff points. If there are short chunks at the end, we combine them with earlier chunks for better coherence. Inspired by RE²G, we implement a dual encoder structure for quick retrieval at a broad level and a cross-encoder for deeper semantic interactions at a more detailed level. We ensure efficient retrieval using FAISS. Next, we address the challenge of long context question answering, where evidence is often spread out. This evidence not only contains knowledge but also shows logical connections between chunks. However, when we retrieve chunks, they may not carry enough global context, and their order might not match the original text, leading to confusion for downstream models. To solve this, we map the short chunks back to their original long context paragraphs using a mapping function. We keep only the paragraph that has the highest similarity to the question when multiple chunks correspond to the same paragraph. This strategy helps us recover relevant context effectively. We then combine these paragraphs and input them into the prompt of our LLM-Augmented Information Extractor, which uses zero-shot in context learning. The prompt guides the model to gather global information enriched with background and structural knowledge. We also introduce a COT-guided filter to improve the relevance of retrieved chunks, especially for complex multi-hop questions. Retrieved chunks often contain redundancy, making it hard to identify which ones are useful. Our filter uses a two-stage approach. In the first stage, we generate a chain of thought, COT, that provides global clues for answering the question. In the second stage, these COTs guide the model to focus on relevant knowledge throughout the reasoning process. This helps us assess the relevance of chunks and identify multi-hop semantic connections, ensuring we accurately filter out irrelevant chunks while retaining important details. The global information we gather includes both background and structural knowledge, while the factual details come from the filtered chunks with minimal noise. Our generator combines these two types of information to produce answers to questions. For instruction tuning, we utilize several leading open-source models, including ChatGLM, Qwen 1.5, Vicuña, Llama 2, and Llama 3, all of which support multiple languages and tasks. We fine-tune these models using high-quality data from LRG instruction, ensuring it is standardized into a QA instruction format. During training, we use the Llama factory library and powerful GPUs, applying advanced training techniques to optimize performance. Section Summary. In this section, we describe our hybrid retriever that segments long context paragraphs into manageable chunks for efficient retrieval, utilizing a dual encoder structure and a mapping strategy to maintain semantic coherence. We also introduce a COT-guided filter to enhance the relevance of retrieved chunks for multi-hop questions, and detail our LLM-Augmented generator that combines global and factual information to produce accurate answers, all while employing advanced instruction tuning techniques on leading LLMs. Section: Experimental Setup. In this section, we describe our experimental setup, datasets, and evaluation methods. We chose 3 challenging multi-hop datasets: Hotpot QA, 2 Wiki multi-hop QA, and Musique from LongBench for our evaluation, instead of using raw datasets. We standardized these datasets for RAG tasks and reported the F1 score as our evaluation metric. The statistics for these datasets are provided in a table. To demonstrate the effectiveness of our LongRAG approach, we compared it against 3 categories of baselines. 1. Long context LLM methods, including LongAlign and LongLORA. 2. Advanced RAG methods, such as CFIC, CRAG, and self-RAG. And 3. Vanilla RAG, which consists of a retriever and generator based on various LLMs. These LLMs range from smaller models, like ChatGLM 3 to 6B32K and Vicuña V1.5 to 7B16K, to larger models like GPT 3.5 Turbo and GLM4. In our experiments, we measured all token lengths using the ChatGLM tokenizer. We evaluated 4 different retrieval strategies to thoroughly analyze LongRAG's performance, represented as chunk size times top K, including combinations like 200 times 7 and 500 times 5, with a default chunk size of 200 words and top K set to 7. For overall performance, we conducted a multi-dimensional comparison, as shown in a table. When comparing LongRAG to long context LLM methods, we aligned the parameter sizes of Llama 2 and found that our system, using supervised fine-tuning, outperformed LongAlign and LongLORA across all datasets. We also noted that LongRAG consistently surpassed other similar-sized LLMs, confirming its effectiveness. This is likely because long context LLMs often miss important details, while LongRAG captures them accurately. When comparing LongRAG to other RAG methods, we found that it achieved an average improvement of 6.16% over advanced RAG methods, particularly self-RAG, which can sometimes amplify decision errors. Additionally, our system showed significant improvements of up to 17.25% over vanilla RAG, as it maintains a coherent long context structure, allowing for better answer generation. We also discovered that LongRAG, whether using fine-tuned small models or non-fine-tuned large models, consistently outperformed baseline methods. Notably, LongRAG with the fine-tuned chat GLM3-6B32K performed better than the non-fine-tuned GPT 3.5 Turbo, demonstrating our system's ability to handle complex long contexts effectively. In our ablation study, we examined 5 strategies to highlight the effectiveness of our information extractor and the COT-guided filter. We found that the RAG-long strategy, which maps back to the original context, did not significantly improve performance compared to RAG-base. The extractor strategy, however, effectively enhances answer quality by first extracting global information and then using it alongside retrieved chunks. The filter alone showed only marginal improvements, as it primarily reduces information. However, when combined with the extractor, the joint strategy of extractor and filter achieved the best performance, providing refined information with less noise. While there were instances where the extractor alone performed better, the filter can enhance performance when the underlying LLM has strong instruction following capabilities. Finally, we noted that not all researchers can afford high-cost API LLMs. Our method allows for the use of more affordable open-source local LLMs before the generator, making it a cost-effective alternative while still achieving competitive performance. Thus, the extractor and filter strategy is essential for balancing performance and cost. Section Summary. In this section, we evaluate our LongRAG system using 3 multi-hop datasets and various baseline models, demonstrating its superior performance through a multidimensional analysis. Our findings indicate that LongRAG consistently outperforms both long-context LLM methods and traditional RAG approaches, particularly due to its effective information extraction and filtering strategies that enhance the quality of generated answers. Section Discussion. In this section, we analyze the trends in token lengths used in our generator, G, across all datasets after applying 5 different strategies. Our findings show a consistent pattern. The E&F strategy uses fewer tokens but yields better results, while the RNL strategy uses the most tokens without significant improvements. This suggests that we can achieve higher quality information with E&F. We also examine component transferability. Here, E&F refers to using chat GLM3-6B32K as the built-in language model for our extractor, E, and filter, F, while G utilizes other strong online language models, such as GPT 3.5 Turbo. When we mention E and F without SFT, we mean that we are using the same built-in language model for E, F, and G. Our results indicate that we can effectively transfer the capabilities of expensive online language models to a more affordable local model, achieving excellent outcomes that surpass GPT 3.5 Turbo and compete with GLM-4.